Okay, so in this video, I wanted to talk about the Hardy-Weinberg equilibrium. But in order to do that, we need to first understand something about evolution first. So in order to set up the background for Hardy-Weinberg, let's go ahead and define what microevolution is. As you guys know, evolution, or descent with modification, is largely divided into micro and macroevolution. With macroevolution, we're looking at things like speciation and how those divergences occur, but in microevolution, it's a little bit more specific. If we wanted to define microevolution, we can simply say that microevolution is, say, something like changes in an allele frequency, which happens over time. So let's go ahead and just make it like this to keep it simple. So changes in an allele frequency over time. And this could be at a particular locus or across many loci. Of course, in reality, it happens across multitude of loci, which then culminate in the phenotypic changes that you see. But just to be a little bit more specific, let's just say an allele frequency to focus on one locus at a time. So that's microevolution. So in order to see how microevolution can be modeled, we can sort of think about something called population genetics. And in population genetics, what we do is instead of looking at the genotype of any given individual, we might be looking at the allele frequencies of the entire population as a whole. So we're not going to be paying attention to any given individual, but looking at all of the alleles that exist in the population. So how do we do that? So let's first define our population as this little box. And it's a model, and we're going to put some individuals in there, but obviously it's not going to be representative of the whole population. But assuming that these are rabbits that live in a population, let's just say that we have two different variants. Let's say that we have a dominant allele called A that allows for rabbits to express a brown fur. And then we have the recessive allele, little a, that allows the rabbits to express white fur. So we have brown rabbits and white rabbits. And in a given population, we might have a brown rabbit, a brown rabbit, a white rabbit, a white rabbit, a white rabbit, brown rabbit, brown rabbit, brown rabbit, white rabbit, and let's just go ahead and write one more white rabbit like this. And even though in this population, we do have these alleles belonging to each individual, when we think about the entire population genetics as a whole, we actually care more about the frequency, let's say frequency of the entire A allele and the frequency of the entire little a allele in this population. So in order to do that, all we have to do is simply count all the alleles that exist. So big A, there's 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 big A alleles here. So that will be something like 8 out of 20 because there are 10 individuals as a whole. So obviously the total number of alleles is going to be 20. And then when it comes to the little a allele, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we have 12 out of 20. And what you'll notice here, and this should be pretty obvious, but these two values, 8 over 20 and 12 over 20, obviously need to add up to 1 because we are looking at the frequency distribution of these two alternate alleles. Now, we are also assuming that there are 2 alleles. I mean, if there are 3 or 4 alleles, then everything would change a little bit, but let's just keep it simple and say there are only 2 allele variants and it's completely dominant. This could be expressed as, of course, 0.40 or 0.60. All right, so this is the population frequency of this is the allele frequency of this population at, so let's say a given time, times 0. All right, so this is important because remember that evolution happens across time. So what we have to understand is that when, say, something like selection or genetic drift or all of these different evolutionary forces occur, they're going to occur across time, which can potentially change these allele frequencies. But the one that's easiest to understand is, of course, natural selection. So let's actually model what natural selection might look like. So for example, let's say that we had a particularly snowy winter. And of course, in these very snowy conditions, being a white rabbit might help you camouflage a little bit better, avoiding predation, thereby leading to greater survival rates and greater reproductive rates. So what we can do is model the predation here by saying, all right, well, this rabbit dies, this rabbit dies, this rabbit dies, this rabbit dies, and this white rabbit dies too, because, things can happen. And what we essentially have are 5 remaining rabbits, which are then going to reproduce. And let's just, for the sake of simplicity, say that they're going to reproduce into the original population of 10. So these guys are going to produce little a. These guys are going to produce big A, little a. Say these guys produce little a, big A, and let's go ahead and make little a there as well. So what we have is now time not 0, but time 1. So if this frequency distribution that we started with is time 0, let's see what we have in time 1. So frequency of the big A allele at this point is going to be 1, 2, 3, and that's it. We have 3 out of 20. And then the frequency of the little a allele is going to be 17 out of 20. So what would that be? That would be something like 0.15 and 0.85 at time 1. And this actually meets our definition of microevolution, because we said that any changes in an allele frequency happening over time is going to be considered microevolution. And what we've just modeled here was natural selection, right? Because remember, what we're talking about is camouflage and how the predation is going to be affecting the white rabbits a little bit less. They're more likely to survive and leave offspring behind that are also white. That's textbook definition of natural selection. So we were able to model microevolution through natural selection. That's good. But you also have to understand that there are 4 other mechanisms through which this can occur. So let's write 1, 2, 3, 4, and 5. And I'll list them out first, and we'll have a brief conversation about each one of them. So while natural selection is the obvious model that we've been using, you also have to know that mutations can cause microevolution in terms of changing the allele frequencies. And same thing with, let's say, gene flow, and let's say genetic drift. And lastly, we have another type of selectional force that we call sexual selection. Okay, so let's clean up that population here for a moment, because we've been killing off some rabbits here, and we have all of these little mating lines. We can get rid of those as well. So if we get rid of the dead rabbits, we have this population at time 1. There we go. And we know what the frequencies of the alleles are. The big A is going to be 0.15, the little a being 0.85. But what if over time you have mutation events in such a way that this little a spontaneously becomes big A? That's clearly going to affect the frequency. Or alternatively, this little a becomes A prime, some other variant of that allele. So that's also going to change the allele frequency. So it's pretty obvious that selection and mutations can change allele frequencies. But same thing with gene flow. See, gene flow is immigration and emigration from a population with other subpopulations. So if a bunch of brown rabbits decided to move into this area, then clearly that's going to change the population genetics. So gene flow is pretty clear in its ability to change allele frequencies in a given population over time. Now, genetic drift is a little bit trickier, but with drift, what we're talking about is random events like natural disasters or founder effect, as in maybe a small subset of this population goes and populates a new area, but those events that are relatively random occur for pretty small populations. But just to give you an example, there could be a case in which a bunch of these rabbits simply died because of a volcanic eruption, leaving only the big A, little a, and the big A behind, and that obviously is going to have a huge impact on the allele frequencies. And lastly, we have sexual selection. Now this one's a little bit tricky, but the major idea here is that the choosier sex, usually in animals that'll be the females, may have a certain preference for particular males, of course their phenotype, and because of that, those males with that particular phenotype and the underlying genotypic alleles would be more likely to survive. So it's working kind of like natural selection, but instead of predation or resources being the limiting factor in survivability, it's about the throttling of reproductive success of males by the choosier females. So that is clearly going to have an effect on the allele frequencies over time. So we've learned about what microevolution is. So how does that relate to the Hardy-Weinberg equilibrium? Well, it turns out that the Hardy-Weinberg equilibrium can be thought of as somewhat of a null hypothesis for evolution. Let me draw that line again. And what the null hypothesis for evolution is that in a Hardy-Weinberg equilibrium, we don't have microevolution occurring. So I'm going to write it like this. No microevolution occurring, which would indicate that the allele frequencies would not change across time if a population is at a Hardy-Weinberg equilibrium. And typically when we do the Hardy-Weinberg, we're not just looking at the entire population, we're usually looking at a particular locus within that genome of a species. So no microevolution happening. But you see, we have to connect these 5 mechanisms of evolution to the Hardy-Weinberg, because if these 5 mechanisms of microevolution is driving or are driving allele frequency changes, then under Hardy-Weinberg equilibrium, none of those 5 mechanisms could be taking place. So let's actually do that here, because we usually talk about 5 conditions of Hardy-Weinberg equilibrium. So if we say that these 5 conditions are true, then the population is going to be at a Hardy-Weinberg equilibrium, at least at a particular locus. And it looks somewhat similar to the list that we have, except it negates each and every one of those mechanisms. For example, we might say no natural selection. That's one of the very important conditions of the Hardy-Weinberg equilibrium. We also say no mutation. We also say no gene flow. So it gets pretty straightforward up to this point. But fourth one is very large population. Now, very large populations are shielded against effects of genetic drift because you don't have these sampling effects that can wipe out a significant portion of the population because you begin with a very large population. So number 4 there is actually negating genetic drift. And then the last one is often called random mating, sometimes called assortative mating. And this, again, as you can see, is negating sexual selection. So if these 5 conditions are true, what do we know? Well, then whatever allele frequencies we have would remain across time, and all that would happen is that those alleles would shuffle randomly within individuals across time. And because of that, we're able to actually come up with a very simple but elegant mathematical model to show how those alleles would manifest as genotypes of individuals in a population. So what does that mean? So first, let's define what the 2 equations are. We have P plus Q is equal to 1, and we have P squared plus 2PQ plus Q squared is equal to 1. You see, P represents the frequency of one of the alleles, maybe that dominant A allele that we saw before, where Q represents the frequency of the recessive allele. And you see how P plus Q is equal to 1? Well, we know that these equal to 1 and these equal to 1. So we've already sort of, laid out the foundations for why that would be the case. But as we said before, if these alleles are simply randomly distributing across populations, then the frequency can also be thought of as the probability of finding that allele in that given population, and the probability of finding those 2 alleles together, which are independent, would be the rule of multiplication, which means that we would have P squared, which represents the frequency of individuals who are homozygous dominant. And little q squared there, would be the frequency of individuals who are homozygous recessive. And this 2pq would represent the frequency of individuals who are big A, little a. And this 2 really is because you have 2 possibilities of big A, little a. You could be little a, big A, or big A, little a, like that. So you have 2pq. And this relationship would stay true across time. So let's do a simple example of how we might apply the Hardy-Weinberg equilibrium on a new page here. So one of the examples that we can look at is something like PKU. So phenylketonuria is a genetic disorder, and usually the question is going to tell you that, look, this PKU is an autosomal recessive disorder. So let's say this is an autosomal recessive disorder, which you should probably already know what that means. It means that if you have little a, or little p, you have that disorder. And they will also tell you that it is at a Hardy-Weinberg equilibrium. And then they give you a little bit more information. But before we do that, let me just rewrite the equations here. There we go. Now they're going to usually tell you something like this. PKU occurs in 1 in 10,000 births. Something like this. And then they'll ask you something like, what % of the population are carriers. Okay, so it almost seems like you have very little information to go by, but we can start by defining some of the parameters that we're given here. So first of all, let's figure out where we want to be. Where we want to be is determining the percent of population that are carriers, and carriers in autosomal recessives are, of course, the heterozygote individuals, so this is where we want to end. So where do we begin? Well, that's right here. And even though this seems a little bit tricky, you can kind of tell that when they say that it happens in 1 in 10,000 births, births represent individuals, which means that 1 in 10,000 is the frequency of homozygous recessive individuals, indicating that where we begin is right here at Q squared. So mathematically speaking, it's very simple. We know what the Q square is, so we figure out the Q, we figure out the P, then by using Q and P, we can figure out what the 2PQ is going to be. And I'll tell you right now that majority of Hardy-Weinberg equilibrium questions are going to give you Q squared as the starting point, and you sort of want to end wherever the question leads you to end at. So here we can say, all right, Q squared is 1 in 10,000, so let's just say 0.001. Okay, actually that's not true, isn't it? 0.0001, which means that Q is 0.01. Okay, so you just take the root of Q squared and you get Q, which means that P is 0.99. 2PQ, well, 2PQ is going to be 2 times 0.01 times 0.99, which I believe is somewhere around 0.0189 or something like that. This math might be wrong. I'm just doing this off the top of my head, but let's just say it's roughly 2%, and that would be your answer. Okay, so 1.89%, 1.9%, 2%, however you want to do this, that's going to be your answer. And if they ask you how many carriers are there in a population of, 1 million, then you say, well, there are 20,000 carriers. You apply that percentage to the overall population. So that's how we do Hardy-Weinberg. And remember, the Hardy-Weinberg is simple in its calculation, but it's predicated on the idea of microevolution and it acting as a null hypothesis for evolution, indicating that evolution is not happening, and then that allows us to model that allele frequency in individuals across time. So hopefully this was helpful, and we'll see you guys next time.